Hello everyone. Over the next few videos we're going to be doing some examples of applying Newton's first law, or the idea of balanced forces and constant velocities, to a series of problems, each with a different kind of wrinkle to it, each with a different kind of complication. Right? The math's going to get a little more intense here, so I'm going to write out lots of steps and things and kind of work through these examples for you before we get to something like a worksheet. Okay? So here's our first one. We have an 11 kilogram box which is being pulled on by a string. Right? It's being pulled with a force of 35 newtons at 40 degrees. Right? So this angle theta here is 40 degrees. But it remains at rest. So you pull on the box, right, with the string, but it doesn't go anywhere. Could happen, right? Box sitting on a table here. Okay, does everybody understand the problem? All right, so although I generally won't ask you to do this in a worksheet, I'd like to start out by doing a system schema just so that we can identify all of the interactions. Then we'll make a force diagram, and then we'll answer some questions. So, if we're going to start out with the box, what is it interacting with? Well, as always, the first thing that we throw in there is the Earth, right? It's interacting with the Earth through the force of gravity, or weight, which after our last lab we now know, right, is the mass times the gravitational field strength, right, mg, right, F of g is mg, is one way to find that. The box is also being supported by the table, otherwise it would fall. Right? We call that support force a normal force. But is that the only thing that's going on? No. Right? With the table, I should say. No. Because if it was, and the box was being pulled on by this string, what would it do? Yeah, it would be moving. Right? It would get moving. So there has to be something keeping it from moving. And that something is, of course, an interaction between the box and the table, which would be friction. Although let's be careful here. Remember that we have two kinds of friction. We have static friction and kinetic friction. Which one is this? Yes, this is static friction, because the box isn't moving with respect to the surface. Okay? In fact, if this box was moving with constant velocity, okay, constant velocity now, not speeding up or slowing down, but if this box was moving with constant velocity, the only thing that would be different in what we're going to do in this problem would be this part. This would be kinetic friction instead of static friction. But other than that, constant velocity is constant velocity, so it wouldn't change anything else. There is one other interaction going on. It's interacting with the string, and that would, of course, be through a force of tension. Now, be careful. I'm not actually, or you aren't actually interacting with the box. You're interacting with the string. So sure, we could put a little circle out here for us and put a connection there, an applied force, but that's not going to affect the box, which is what we're focused on here. So you'll notice that there are 4 interactions, and therefore 4 forces acting upon the box. So again, a system schema is really just to kind of talk our way through the interactions. This is a part that's going to kind of disappear as we go. I'll still do them probably in our examples in this unit, but the force diagrams are really the things that help set up the math. So that's our next part here. So part A, let's draw a force diagram. So when we have problems like this where one of the forces is at an angle, it always helps to start with that force, and you'll see why in a moment. Okay, so let's draw that force of tension at a 40-degree angle. See how that's the same angle as my diagram? Now here's the problem with this force at an angle. It's not just horizontal or just vertical. It's both. Right? Some of this force is pulling horizontally on the box. Some is pulling vertically on the box. So then how do we deal with it? We find out how much is horizontal and how much is vertical. Remember breaking a component or resolving a vector into its perpendicular components? Right? Resolving a vector into its perpendicular components. So we can take this f of t and we can break it down into, there's the angle, f of tx. This is the horizontal component of the force of tension. And f of ty. This is the vertical component of the force of tension. Right? This is why we're going to draw the ones at angles first so that we can kind of see what's really going on horizontally and vertically. Everyone okay with that? And of course, we could do right triangle trig on it later, right, when we need to do the math. Next force I'd like to put on here is the normal force, right? That's a support force, so that will act up perpendicular to the surfaces. And then the next one is the force of gravity. Now, question then becomes, well, how big should that force of gravity be? I mean, yes, we can calculate how big it is, but how big should it be compared to the other forces? Well, let's take a look at the vertical forces that we have acting. How many do you see on our force diagram? How many vertical forces? There's 3. Right? You can't forget that the force of tension partially is pulling upward, F of Ty. So there are 3 vertical forces. Well, does the box have a constant velocity vertically? Yeah, it's not even moving. Right? So that means what has to be true about these 3 vertical forces? They have to balance. Right? They have to be in balance. And since these 2 are pointing up and that one's pointing down, right, the force of gravity has to balance out both the normal force and F of Ty. This is why we need to know how much of the force of tension is vertical, so that we can do these little balancing Newton's first law things. And if you look at my diagram, you can see that, right? If we took this arrow and this arrow together, we'd get the force of gravity arrow lengthwise. And if you're drawing your diagram on a piece of lined paper, it might be easier for you to do that, but you should try to make these, right, balance out in your diagram. So the last force that we have to draw on is the force of static friction. Forces of static friction oppose the attempted motion, so we're attempting to pull the box to the right across the table, so the force of static friction will act to the left. But how big does that force of static friction need to be? Well, it's horizontal, right? And because the box isn't moving at a constant velocity, the horizontal forces need to be balanced. And we now only have 2 horizontal forces, the force of static friction and the horizontal component of the force of tension. Again, why we do that first. And so those 2 forces must balance because it also has a constant velocity horizontally. See the little x means horizontal. So note how much information we get about the forces and their relative sizes by drawing a proper force diagram. Okay? If you actually go through these questions while you're drawing the force diagram, right? What forces are there? What direction are they acting? How big should they be in relation to one another? You're really doing all of the physics. Every other question we can ask after that becomes kind of like a math question, all right? But a good force diagram is invaluable to being able to do these problems. Okay, can't stress that enough. So, now that we got this beautiful force diagram, let's answer some questions about it. So first, I'm going to ask you to write an equation for the horizontal forces and components asking on the box, which we just did, right? We know these 2 have to balance because it's got a constant horizontal velocity of 0. Well, now I want to know how big is that force of static friction? Well, as you see from the equation that we wrote, right, if we want to know how big the force of static friction is, we can figure out how big the horizontal component of the force of tension is. Well, we don't know that yet. We do, however, know the force of tension, it's 35 newtons, and we know this angle, 40 degrees. So with a little right triangle trig, we can figure out the force of tension, horizontal. Now, which trig function should we use to do that? I'm going to show some steps here, which if you're really good at trig, you can skip these steps, right? But I'm going to show them to you here, so feel free to use them. Well, look at the angle right here. Is f of tx the adjacent side or the opposite side? It is the adjacent side. So what trig function relates what we know, the hypotenuse and the angle, to what we're trying to find out, the adjacent side. That's right, the cosine does. Right? Cosine is adjacent side over hypotenuse. One step of algebra to move the force of tension to the other side. Since it's dividing, we multiply. And we get a way to calculate f of tx. Now, could you plug numbers in and find a number? Sure. Okay. I'm going to work these problems symbolically. That's something I like to do. It's kind of a higher level math thing to do. Do you have to do that? No. Right? But it helps. You're going to see it on my keys worked out this way. All right. And if any of you are thinking about going on in physics, taking AP Physics C, say, for example, you're going to have to be able to work symbolically. So it may not be a bad habit to get into. I know it's a lot of writing, a lot of symbols, right? But it's a little more rigorous way to do the problem. So I'm going to substitute that in there, that expression. And then I can calculate the force of static friction by taking the force of tension times the cosine of the angle. At this point, I've got all those, right? So I plug them in. I make sure my calculator is in degrees and not radians if you're in trig class at the same time as this class. And I get to 2 sig figs because there's 2 there, there's 2 there, and there's 2 there. See the decimal point? Right? So this 0 counts. So I'm going to have 2 in my answer. It's 27 newtons. So that's f of tx and how much static friction we must have. Okay with that? A little bit more math, a little bit of right triangle trig, right? But we got to work our way through it. Part C, just for kicks. I want to figure out how much normal force there is. How much is the table supporting the box? Well, that's a vertical thing, so we need to write an equation for the vertical forces, but didn't we do that already? Right? We said there's 3 of them, normal force, gravity, f of ty, the y component of the force of tension, and those have to balance because the velocity is constant, 0, and therefore the downward force of gravity has to balance out the normal force and f of ty. Note, by the way, how I've taken the arrows off because you're just relating the sizes of them now. And that's because the vertical velocity is also constant, 0. So we're trying to solve this. So first step of algebra, we've got to move this, right? We do the opposite thing, so we subtract. By the way, I also flipped the sides, all right? Technically the reflexive property of equality, because I like having what I'm solving for on the left. You can leave it on the right, doesn't really matter. Now, we don't know f of ty, but we do know f of t in the angle, so we can do some right triangle trig there. Do we know the force of gravity? No. We know that the box is 11 kilograms, but kilograms are units of what? Mass, right? So we know the mass of the box, not the weight of the box, the force of gravity acting on the box, right? The hint there, it might be one of 2 things. I might tell you, right? I could have been nice and said a box of mass 11 kilograms, right? But it's contextual. It's the units. That's why we use units, right? Units give these things context. If I meant for it to be the force of gravity, it would have been in newtons, or I would have said like a box weighing so many newtons. But remember, we can convert there. So, a couple of substitutions then. This time we're going to use the sine function because the vertical component of the force of tension is the opposite side to the angle, right? Sine of theta is opposite side over hypotenuse. Opposite over hypotenuse. 1 step of algebra to move this over since it's divided by. Right? We get that. That we can plug in right here. But again, we have to also convert from mass to force of gravity. So hopefully you're going to get used to this one because we're going to do this a lot this year. All right, the force of gravity, F of g, is also mg. Mass times gravitational field strength. This is not gravity. Gravity is a force. This is the force of gravity. This is the gravitational field strength. I know it's a mouthful, right? But that's what it is. Okay, so we can substitute that in right there. And then we get this equation. That the normal force is mg minus f of t sine theta. Now again, I like working symbolically, plugging all my numbers in at the end. If you went off to the side and calculated the force of gravity, went off to the side, figured out f of ty, and just kind of plugged those numbers in up here, would you be wrong? No, heck no. Go ahead. Right? You still have to kind of do this work to find those things. Okay? But, if you can work symbolically, try to take it to that level. So we plug all of the numbers in. Note the units have to work out. The kilogram here cancels with the kilogram there, so we're left with newtons. This is already in newtons since the sign doesn't have any units to it. Be careful that you're in degrees. Note that everything has 2 sig figs, and so our answer will have 2 sig figs, and we get 85 newtons. Now notice here, the force of gravity is a little above 100 newtons. Right? It's almost 110. This is 9.8, so a little bit less than that, right? So notice that this normal force is smaller than the force of gravity, right? Which is what we set up here on our force diagram, because you partially were lifting up on the box with the force of tension, where the string was. So we make sure here that we're doing our physics correctly and our math correctly, right, by checking out whether our answer makes sense with what we've done in the force diagram. Again, really can't stress how important it is to draw force diagrams where you take the time to think your way through the force diagram and apply the physics. Right? It then becomes a math problem afterwards. Not that it's trivial math anymore. Right? The math's getting a little heavier in here. Right? But the physics is locked into your questions and your answers here in the force diagram. So have fun applying this, right, in the next worksheet.